In this lesson, we're going to learn about colligative properties. Antifreeze is added to water in your car's cooling system to help the water boil at a temperature higher than 100 degrees Celsius and to make it freeze at a temperature lower than 0 degrees Celsius, right? We don't want the water in your car to be boiling away or to be freezing due to extreme temperatures. So if you add something to the water in your cooling system, like antifreeze, we end up with what's called a boiling point elevation, and we end up with a freezing point depression. It basically extends the range of temperatures that water will remain a liquid. Instead of 100 degrees range between 0 and 100 of water staying a liquid, we might be able to get water to stay a liquid from negative 20 or 30 degrees Celsius all the way up to 120 degrees Celsius. Also, road salt can be added to road surfaces in the winter to help melt the ice due to an exothermic reaction as the salt is dissolving. But then once the salt is dissolved, the freezing point of water will go lower, go down, and that'll help keep the water from freezing. So what's going on here? How does adding something to water cause the water to change the temperatures at which the water boils and freezes? The short answer to that question is something called colligative properties. A colligative property is a property of a solution that is dependent upon the ratio between the total number of solute particles dissolved in the solution to the total number of solvent particles, typically water. And what's fascinating is that colligative properties depend on how many solute particles are actually dissolved in a solution, right? It's dependent on how many solute particles are dissolved in a solution. Colligative properties do not depend on the specific identity of the solute. Right? So it doesn't matter if the solute is polar or nonpolar or ionic. It just depends on how many particles you can get dissolved into solution. So the specific properties we're going to try to explain are boiling point elevation, freezing point depression. The freezing point is going to go lower than 0 degrees Celsius, and vapor pressure depression. Vapor pressure will also decrease. All of these, the elevation and depression, increases the range of temperatures that water remains a liquid. So basically, the more particles of solute that dissolve into the water, the more those solute particles are in the water's way. This is how boiling point, vapor pressure, and freezing point are changed. Boiling point. If solute particles are blocking water vapor from escaping the liquid water, it will take more energy to make the water boil. So the boiling point temperature will increase to some temperature above 100 degrees Celsius. Vapor pressure. If the solute particles are blocking the water vapor from escaping the liquid water, the pressure exerted by those water vapor particles will naturally have to decrease. If you can't get water into the gas phase, then you don't have gaseous particles or as many gaseous particles present in the vapor phase in order to even exert vapor pressure. Freezing point. If you have solute particles blocking the liquid water from coming together in the solid form, it will require that the water molecules slow down enough to make the water freeze, and the freezing point temperature will decrease to some temperature below 0 degrees Celsius. So, if colligative properties are dependent on the number of dissolved particles, how do you get more solute particles dissolved into the water? Well, simply you could just add more solute, right? Make the solution more concentrated. That's one way to do it. Or you could choose your solute carefully. If you choose a non-electrolyte, right, These are covalent compounds that do not break apart into ions. So for every mole of solute you dissolve, you will have 1 mole of particles dissolved in the water. For example, for one of these, this is sucrose, just table sugar. Okay, if you have 1 mole of sucrose particles in the solid form and you dissolve them in water, you are going to have 1 mole of sucrose particles dissolved in the water, right? So for every particle you put into the water, you will have exactly that number of particles actually dissolved in the water. However, when you add electrolytes, which are essentially just ionic compounds, they do break apart into ions. So for every mole of solute you dissolve, you're going to have greater than 1 mole of particles actually dissolved in the water, depending on the number of ions in the chemical formula, right? So if you add 1 mole of sodium chloride, it's going to break apart into sodium ions and chloride ions. So one of these NaCl's is going to break apart into 2 moles of particles that are actually dissolved in the water. Calcium bromide, for every one of these particles that you put into the water, it's going to break apart into a calcium ion and 2 bromide ions for a total of 3 moles of particles. AlF3, for every one of these, it's going to break apart into 1 aluminum ion plus 3 fluoride ions for a total of 4 moles of particles that will be dissolved in water. Calcium nitrate, CaNO3 is going to break apart into a calcium ion and 2 nitrate ions for a total of 3 moles of particles. Every one of these, you're going to get 3 particles dissolved in water. Now, how about this one? Aluminum sulfate is going to break apart into 2 aluminum ions plus 3 sulfate ions for a total of 5 moles of particles. So electrolytes, because of their solubility and because they will break apart into multiple particles, you can get a lot more particles dissolved in water if you start with an electrolyte that naturally breaks apart into multiple particles. So let's try some applied questions. Considering the 4 solutions, if you have 100 grams of solute, right? So the quantity of solute in all 4 of these is remaining the same. But you're going to dissolve each one of these situations. You are going to put them in a different amount of water. Okay. So what do we have here? We have this first solution, which is the least concentrated. And as we go down here, we are going to get a solution that is most concentrated. Okay. And so the solution that will have the greatest impact on the colligative properties will be the solution that is the most concentrated. Okay. Regardless of how many particles get dissolved, we're actually looking at essentially the molarity or the concentration. So which solution will boil at the highest temperature? That's going to be the most concentrated solution. And so we're going to say that that's solution D, right? It's the most solute in the least amount of water. Okay. Now, which solution will boil at the lowest temperature? You're going to look for the least concentrated. Okay. And of course, that's going to be solution A. Now, that's because boiling point, the more particles you have dissolved in the solution, the given solution, that'll make the boiling point go the highest because it's boiling point elevation. Freezing point, on the other hand, is freezing point depression. So the solution that's going to freeze at the lowest temperature, you are looking for the most concentrated solution, and we know that to be solution D. Which solution will freeze at the highest temperature? Still below 0. Right? Still below 0, but the highest of all these will be the least concentrated solution, and we know that to be solution A. All right, so in this situation, we had the same amount of solute, we just changed the amount of the volume of solution total, and that's how we varied the concentration of the solution. In our next example, we have the same amount of solute and the same amount of water. So what we are looking at here is the number of particles that each one of these dissolves into, right? So MgF2 is going to break apart into a magnesium ion and 2 fluorides, right? So a total of 3 particles dissolved in water. AlCl3 is going to break apart into an aluminum ion plus 3 chlorides for a total of 4 particles. C6H12O6, being a molecular compound, a covalent compound, won't break apart at all into any particles. It'll just stay as the one particle that you put in. And then KBr is going to separate into a potassium ion and a bromide ion for a total of 2 particles dissolved, right? So the solute that will have the greatest impact will be the solute that breaks into 4 particles. The solute that has the least impact to all the colligative properties is going to be the non-electrolyte that maintains the 1 particle that you put in. So the solution that will boil at the highest temperature will be the most solute particles in solution, which is aluminum chloride, and so we would have to say solution B. Which solution will boil at the lowest temperature? Now, when we say lowest, remember this will still be above 100 degrees Celsius, but it'll boil at the lowest temperature when it has the fewest solute particles in solution. Okay, and the fewest here is solution C. Which solution will freeze at the lowest temperature? Again, the lowest temperature will be the solute that breaks apart into the most particles, right? So the most particles will have the greatest depression on the freezing point. So that's going to be solution B with 4 particles. Which solution will freeze at the highest temperature, but still below 0, will be the solution that has the fewest or the least particles. And we know that to be solution C. So what we have learned about is that colligative properties are properties that are only impacted by the number of particles dissolved in water, not by the identity of the particles. We know that colligative properties are boiling point will become elevated, the freezing point will be depressed or lowered, and the vapor pressure will also be decreased. And that is going to depend on the total concentration of solution, and you can choose your solute carefully. If you want to maximize the number of particles in solution, you would choose an electrolyte, and you would choose an electrolyte that breaks apart into the most ions. If you're looking for a solution that has the least impact on freezing point or boiling point or vapor pressure, you would choose a non-electrolyte, like a covalent compound. All right, that's it for this lesson. We'll see you back in the classroom.